Okay, so welcome to this next video in the playlist on lipid metabolism. In this video, what we're going to talk about is cholesterol biosynthesis. Okay, so we're going to talk about the biosynthetic pathway by which cells can synthesize cholesterol. Okay, right. So the structure for this video then, we're going to start off by discussing a few little prerequisites. So for instance, we'll discuss the structure of cholesterol. We're then going to discuss something about acids and conjugate bases, because that's something that's going to be a running theme throughout all metabolic pathways, that you have acids and then you have their conjugate bases, and nearly always it's the conjugate bases which are present in the highest amount within the cells and are therefore taking part in the reaction. We're then also going to talk about the molecules nicotinamide adenine dinucleotide and nicotinamide adenine dinucleotide phosphate, NAD and NADP. Okay, and then we'll begin by looking at the way that you get acetyl coenzyme A, which is the starting point for the synthesis of cholesterol, out of the matrix of mitochondria into the cytoplasm, and then we'll begin the pathway. Okay, right. So let's begin with the structure of cholesterol then. So cholesterol is a sterol, and all sterols are steroids. Okay, so we'll begin with what a steroid is. So basically, steroids have a fixed chemical structure within them. So this is something that surprises people often when they hear it for the first time, that the definition of a steroid is not a biological one. So it's not, a molecule with a certain biological activity. Instead, it's actually a chemical one. It's steroids are classified according to their chemical structures. Okay, so let me show you the structure of a steroid. So all steroid molecules have this conserved structure within them. So they have 4 carbon rings, 3 of which are 6-membered and 1 of which is a 5-membered carbon ring. Okay, so here's the next 6-membered carbon ring. And also, when people talk about steroids and draw the structure of steroids, they absolutely always do it in skeletal formula rather than molecular formula, and that's just because the structure of a steroid looks extremely simple when you show it in skeletal form, whereas it looks extremely complicated if you show it in molecular form. So remember, in skeletal formula you don't show carbon atoms. Instead, carbon atoms are implicitly shown by corners and by the coming together of many different bonds. Okay, so all of these sort of points are carbon atoms. You also don't show hydrogen atoms coming off carbon atoms. Okay, so whenever you've got missing bonds of carbon atoms, those are implicitly to hydrogen atoms. Now, the basic pure steroid structure looks so simple in skeletal format because all that you have within it are carbon atoms bound to other carbon atoms, with then hydrogen atoms coming off the carbon atoms. So let me just now finish this steroid structure by putting the 5-membered carbon ring over here. Okay, so that's the structure of a pure steroid here. Okay, now to turn a steroid into a sterol, what you do is you have an alcohol group coming off this carbon down here. Okay, so originally that carbon would have had 2 hydrogen atoms coming off it. You take one of those hydrogen atoms off and put an alcohol group on. That gives you a sterol structure. Okay, so all sterols have this conserved structure within them. Okay, right. So how do we turn this generic sterol into a cholesterol molecule? Well, basically, to turn it into cholesterol, what you do is you add on methyl groups of this carbon and this carbon, turn this into a double bond, and then add a little group on there. But before we do that, I just want to discuss a little bit more about steroid terminology. Okay, so this first ring of a steroid here is called the A ring. This second one is called the B ring. This third one is called the C ring, and this fourth one is called the D ring. In addition, if you want to know how to number the carbons of a steroid molecule, basically this one, you start with this one up here and call that number 1. This one you call number 2. This one 3, 4, and then you go round 5, 6, 7, 8, 9, 10. Okay, then you continue on up here, 11, 12, 13, 14, 15, 16, and then 17. So that's how the carbons of a steroid or sterol structure are numbered, basically. Okay, so now let's turn this into cholesterol. So let's draw it out again, and then we'll turn it into cholesterol. Okay, right, so we have a 6-membered carbon ring here, that's the A ring. Then we have our alcohol group coming off the A ring here. Then we have the B ring here. Okay, and then we have a methyl group coming off this 10th carbon here. So you take a hydrogen off that 10th carbon and you add a methyl group on instead. Okay, then we have our C ring up here. Okay, and you can see hopefully now how this notation, this nomenclature is quite helpful. Okay, and we're going to have a methyl group coming off this 13th carbon here. And then we've got our 5-membered carbon ring here, which is our D ring. And we're also going to have a double bond between the 5th and the 6th carbon down here. And we're also going to stick a great big side chain off this 17th carbon up here. So we're going to stick a 7-carbon side chain off. So 1, 2, 3, 4, 5, 6, 7. Okay, like so. And we'll attach this 17th carbon to the 2nd carbon of that 7-carbon side chain there. And then off the 6th carbon, we'll then have a methyl group coming off like so. Okay, so this molecule is then called cholesterol. Okay, right. So that's the structure of cholesterol then. That's what we're going to be trying to make. Now, obviously we've got more carbons now in cholesterol than we had in the original sterol molecule down here. So what I now want to do is revisit the numbering system for the carbons within a steroid structure and extend our numbering system so that it includes the carbons of these methyl groups and then the carbons of this side chain up here. So, this carbon is still called 1, then we've got 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we've got 11, 12, 13, 14, 15, 16, 17. Then you go, so we stick with the same nomenclature as we've always used for steroids. Then we sort of start with the additional things that we've added on. So we start with this one here, we call that 18. Then we call this one 19. We call this one here 20. This one then is 21. This one then is 22, 23, 24. And then we have 25 here. And then you can name one of these 26 and the other 27. Okay, right, so that's the numbering system for the carbons within a cholesterol molecule. Okay, so there's the structure of cholesterol. That's what we're going to see how cells make within this video. Okay, now the next prerequisite I want to do before starting the biosynthetic pathway is I want to talk about the difference between an acid and its conjugate base. Okay, so basically, an acid is a molecule which is capable of donating protons into solution. So let me give you an example of an acid that we're going to see within this video. Okay, so, well actually, we're going to see the conjugate base of this acid within this video. Okay, so, this is pyruvic acid, okay? So it's a 3-carbon molecule where you have a carboxylic acid at one end and then a ketone group in the middle of the molecule like so. So this is pyruvic acid. Okay, so this is an acid molecule because that proton that comes off the alcohol group of the carboxylic acid group can be donated away into the solution basically. Okay, and when it does that, that will increase the acidity of the solution. Okay, right. Now, when pyruvic acid actually donates its proton away, what will it actually become? Let's draw out the molecule of pyruvic acid once it's actually lost that proton then. Okay, so Once the proton has dissociated away from the oxygen of the alcohol group of the pyruvic acid molecule, you are left with the conjugate base of pyruvic acid. Okay, so the conjugate base of an acid means the acid, once it has lost its proton, and what's left is going to be left with a negative charge. This molecule is then called pyruvate. Okay, so the strict difference between pyruvic acid and pyruvate is that pyruvate is the conjugate base of the pyruvic acid molecules. Okay, so this is a running theme for all acids, that they can give away their protons to the solution, and when they do that, they get a negative charge themselves, and they are then no longer actually acid molecules. This is not an acid anymore. It is not capable of donating protons into the solution, therefore it doesn't satisfy the definition of an acid. Okay? Instead, it's actually a base, because instead of donating protons away into the solution, it's actually capable of receiving protons from the solution. So protons within the solution can then bind to this negatively charged oxygen here to recreate the alcohol group, and therefore it can actually accept protons from the solution, and it's a conjugate base. And that's not just something that occurs for pyruvic acid, that's true for all acids, that once they've donated the proton away, what is left is called a conjugate base, and it's generally not an acid anymore. Instead, it's actually capable of receiving protons, therefore it's a base molecule. Okay, right, so we're going to see this sort of thing happening all the time. We're going to be working with acid molecules, and these acid molecules within the normal physiological pH of cytoplasm will actually donate their proton away and become the conjugate base. So we're often going to be working with the conjugate bases when we look at these biosynthetic pathways, which is why people generally talk about pyruvate rather than pyruvic acid, because most of the molecules in the cytoplasm will exist as pyruvate rather than pyruvic acid, because they'll have donated away their protons at physiological pH of around 7.5. Okay, right. So that's the difference between an acid and its conjugate base, and that's an important concept for working with the biosynthetic pathways. Okay, right. So the next thing I want to turn my attention to is what NAD, nicotinamide adenine dinucleotide, and NADP are, nicotinamide adenine dinucleotide phosphate. Okay, so basically these things are capable of transporting electrons. Okay, so let's write out their name in full. So NAD plus stands for nicotinamide, okay, and then adenine dinucleotide. So the A is for adenine, and then the D is for dinucleotide. So nicotinamide adenine dinucleotide. Okay, right. So basically, this molecule, nicotinamide adenine dinucleotide, is capable of accepting something called a hydride anion. Okay, so a hydrogen atom with a negative charge is called a hydride anion. Okay, so it's quite rare to see something like this. Usually we see hydrogen atoms with a positive charge, where the hydrogen atom has lost its electron and therefore now has a positive charge. Okay, so let me just remind you of the basic structure of a hydrogen atom. Okay, so generally the normal isotope of hydrogen only has a single particle in its nucleus, which is a proton. Okay, so I'll colour this in red here. Okay, obviously there are different isotopes of hydrogen where you have differing numbers of neutrons within the nucleus of hydrogen, but generally the main isotope of hydrogen that you find within the world is protium, where you only have a single proton within the nucleus and no neutrons. Okay, and then orbiting the proton you then have an electron like so. Okay, so this is a hydrogen atom. So this is hydrogen atom. Okay, right. So basically what can happen is this hydrogen atom can donate its electron away, and then it becomes a hydrogen cation, which is effectively just a proton, because once you've donated the electron away, all you are is your nucleus, okay, which is this single proton. Right. However, you can actually add another electron in here. So we'll put another electron there, okay, and that will create you what's known as a hydride anion. So when you give a hydrogen atom another electron, you give it a negative charge, and that's called a hydride anion. So basically, nicotinamide adenine dinucleotide and nicotinamide adenine dinucleotide phosphate can accept these hydride anions. Okay, so let me show you the structure of nicotinamide adenine dinucleotide, or at least a cartoon of the structure. We're not going to draw the structure out in full. We'll draw a little cartoon. Okay, so basically you have an adenine organic base bound to a ribose sugar. Okay, so here is the adenine organic base, and here is a ribose sugar. Okay, so I'm going to colour these in. So here is the ribose sugar in blue here, and then we've got an adenine organic base in green here. Okay, and basically what you are then going to have is two phosphate groups coming off the alcohol group of the fifth carbon of the ribose sugar. So here is one phosphate, here is the second, and then this second phosphate is also going to be attached to the fifth carbon of another ribose sugar here. Okay, so let me draw that here. So that was supposed to be the fifth carbon of this second ribose sugar here. And this second ribose sugar is going to have nicotinamide attached to it. So I'll just put an N there. Okay, so this is the structure of nicotinamide adenine dinucleotide. So the reason it's called that is we have nicotinamide, then we have adenine, and then we have this dinucleotide structure here where you have a ribose sugar bound to a phosphate group and then a ribose sugar bound to a phosphate group, like so, and that's why it's called nicotinamide adenine dinucleotide. Okay, so here is the other ribose sugar here in blue. Okay, and then let me colour in those phosphate groups there, one, and here's the second one here. So that's a nicotinamide adenine dinucleotide molecule, and basically around the nicotinamide you have a positive charge usually, okay? Right, and that's on the nitrogen atom of the nicotinamide molecule. So what can happen is this molecule can accept a hydride anion, i.e. it can accept a proton and two electrons, and clearly that will neutralize this nicotinamide adenine dinucleotide molecule. Okay, it is then called NADH, okay, because it has accepted one proton and two electrons, so it's effectively accepted a single hydrogen atom with an extra electron, and that's why it's called NADH, to show that you've got one hydrogen here. Okay, so this is sometimes called reduced nicotinamide adenine dinucleotide, or reduced NAD is probably more common. Okay, right. Now, it's very similar for nicotinamide adenine dinucleotide phosphate, or NADP. Okay, so this is just exactly the same. It's nicotinamide adenine dinucleotide, and then on the end you have a phosphate. Okay, right, so where do you add on the phosphate group onto this structure here? Well, basically you add the phosphate group in down here on the ribose sugar of the adenine nucleotide here. Okay, right. So this little ball here will represent another phosphate group. Right, so that's the structure of nicotinamide adenine dinucleotide phosphate, or at least that's a cartoon of the structure. So we have nicotinamide here bound to a ribose sugar, bound to a phosphate group, then we've got another phosphate group bound to that phosphate group, and then bound to that other phosphate group we have a ribose sugar with an adenine organic base here. Okay, and that's the structure of nicotinamide adenine dinucleotide, and to turn it into nicotinamide adenine dinucleotide phosphate, you just stick a phosphate group there. And effectively the function of nicotinamide adenine dinucleotide phosphate is exactly the same as that of nicotinamide adenine dinucleotide. It can accept a hydride anion, and then later when it's called upon, it can give that hydride anion back up to another reaction. Okay, right, so these are effectively collecting electrons, basically, because this structure has a single proton and then 2 electrons, okay? So they act as electron transporters, basically. Okay, and again, when you have the reduced form of NADP, then you put NADPH, which is the nicotinamide adenine dinucleotide phosphate molecule with a hydride anion attached to it, okay? And this is reduced NADP. Okay, right. So, that's the electron carriers done. Let's now turn our attention to how you get acetyl coenzyme A out of the matrix of the mitochondrion, because basically the entire of cholesterol biosynthesis is going to start with acetyl coenzyme A, but currently acetyl coenzyme A is in the matrix of the mitochondrion, so we need to look at the pathway by which acetyl CoA gets out of the mitochondrion into the cytoplasm, because the cytoplasm is the site of cholesterol biosynthesis. It doesn't occur within the matrix of the mitochondrion, it all occurs within the cytoplasm. Okay, but we'll look at the pathways by which we get acetyl coenzyme A out of the matrix of the mitochondrion and into the cytoplasm in the next video.